So let's discuss thermal stresses. So we know that as you are applying a change in temperature, there will be a change in length, and this then has to do with the thermal coefficient of expansion. But we also know that stress and strain, I guess I'm using little e for this, little strain, are related. So the thermal stresses due to this strain are E, Young's modulus, L delta T. And this is important. This is important because materials, and particularly like in processing or in application, will go through thermal stresses. Materials that are repeatedly heated and cooled, these stresses do contribute to fatigue, and they contribute to crack growth. Stresses build up in a material also due to thermal gradients. So a material that goes through a thermal quench, for example, the exterior may be cool, but the interior is still hot. And in that case, the thermal stresses can approximately be written as the thermal coefficient of expansion, E, the thermal gradient between the interior and the exterior. So we call this a quench gradient. And 1 minus 2 nu. That's the Poisson ratio. So this is just kind of a bulk thermal stress due to quenching. Certainly there will be geometric effects if you have stress concentrators that will play a role. And taking a material and putting it through thermal cycling, it may undergo thermal shock. And we talk about thermal shock in terms of the retained strength. So if I take a part and I heat it up and then I quench it, and I measure the strength of that material or the strength of the part, how much of the strength that it initially had, or that family of parts had before, is retained. So for different quench distances, you'll actually see something which does this. Like that. This is the point, delta C, TC. That is the critical quench gradient for the part to fail, or for the family of parts to fail. And a lot of that has to do with the thermal coefficient of expansion, the overall elastic behavior, but also excuse me, the geometry and the surface of the part. We characterize a material's resistance to thermal shock in terms of the thermal shock tolerance. And we have a figure of merit for that. thermal shock tolerance goes as the tensile strength of the material divided by the coefficient of thermal expansion and it's going to be E modulus of elasticity and the thermal conductivity. You can certainly imagine that material which is stronger will have greater tolerance, greater tensile strength. Higher conductivity will give tolerance because that thermal gradient will dissipate faster. It will be inversely proportional to the thermal expansion. Materials that have a larger thermal expansion will be less tolerant because that gradient will necessarily lead to a larger thermal stress, right? Those are proportional. And the modulus elasticity, again, that has to do with the change in stress and strain. And again, the thermal stress is associated with the directly proportional to the elastic constant in the same way. If you think about the simple linear case, the thermal stress is directly proportional to the thermal coefficient of expansion and the Young's modulus.